Yesterday we talked about an experiment performed by Charles Augustin de Coulomb, which found for us the relationship between the electrostatic force of attraction or repulsion and the magnitudes of the charges involved and the distance that separates those two charges. And the experiment looked something like this. We would have had a thin string or a thin wire hanging from something. And on the end of that thin string or wire was a little rod. And on the end of that rod were two little objects. One of them was charged. We'll call it Q1. The other one doesn't matter if it had a charge or not. It was irrelevant. Now, we were going to bring, or Coulomb would have brought another charge that we call Q2 nearby. Now, he has to measure a few different things, 4 different variables, in fact. He has to measure the value of R. That's the distance that separates the two charges. And that's easy. He can just use a ruler or something like a ruler to measure that value of R. He also has to measure the value of Q1 and Q2. And we talked about this yesterday a little bit, right? He couldn't directly measure the value in coulombs of Q1 and Q2. The unit for charge Coulomb didn't even exist, right? At that time. It got named after him later on. So what he does to manipulate Q1 and to manipulate Q2 is to repeatedly touch a charge against a neutral object. So if he wants to manipulate Q1, then he touches Q1 against a neutral object and it becomes a half Q1. And then he touches it against another neutral object and it becomes a quarter Q1. And then he touches it against another neutral object and becomes an eighth Q1, and so on and so on and so on. So he is able to manipulate the value of the charges without knowing what the actual numerical value is, but knowing what the relative value is. Relative to the initial charge, okay, what is it, right? So that works. To get us a relationship, that works. Now, the value of F, he simply looked at how much the string or the wire twisted, right? The more it twists, the more the force was required to do that. So he was able to measure the value of the force by the amount of twisting of the string. Twisting, or the twisting properties of the string, or the torsional properties of the string. And what he finds is this. When he does the first experiment and manipulates the value of Q1, sees how F responds to that, while the whole time keeping Q2 and R constant as our control variables, he finds that the relationship between F and Q1 is a linear relationship. In other words, as Q1 doubles, then F is going to double. As Q1 goes up by a factor of 13.5, then F is going to go up by a factor of 13.5. It's a linear relationship. Next, he manipulates the value of Q2, sees how F responds to that. What does he got to keep constant this time? Q1 and R. He plots a graph of that data and gets, once again, a linear relationship. So F is related directly this time to Q2. And then finally, he performs another experiment where he manipulates the value of R. Sees how F responds to that. What do you got to keep constant here? Q1 and Q2. Like, there's other things that you hold constant as well, right? But these are the critical control variables. When we talk in our labs about, make sure you list the really important ones. These are the really important ones. What does he get when he plots that graph? This one looks something like this, which on the surface could be a 1 over R or a 1 over R squared relationship, but with a little bit more analysis that you'll do tomorrow in your activity, you would find that this relationship would be a 1 over R squared relationship. So Coulomb takes these 3 relationships that he determined and puts them together. He says that F is related to Q1 and Q2 and 1 over R squared, or in other words, F, the attractive or repulsive force between two charges, is equal to a constant K times Q1, Q2 over R squared. Now, let's identify what each of these variables mean, the units, and then we'll do a calculation with it. Q1 and Q2, those are the values of the charges. And it doesn't matter what order you list them in. Like, let's say you guys are the two charges here. Okay, we won't say whether it's an attractive force or a repulsive force, but you guys are the two charges, okay? It doesn't matter, you have a value of 2, you have a value of 3. It doesn't matter whether I multiply 2 by 3 or 3 by 2, we end up getting the same value, right? It's 6. So whichever one is Q1, whichever one is Q2 doesn't make any difference in the world, okay? Just include both charges there. In coulombs. And remember that we often see the charge in the context of these questions listed as microcoulombs or millicoulombs or something else because coulomb is a big unit of charge. So be aware of that. R will be the separation distance. Just like in physics 20 when we were doing Newton's law of universal gravitation, it's really the distance between the center of the two objects. Do you remember that? That was more important, though, with gravity, to be honest, because with gravity you were dealing with sometimes really big objects. What's the force of gravity between the Earth and the Sun? Well, the Sun and the Earth are so big that the distance from the center to the surface is significant. It mattered, right? Here, you were usually dealing with things that are small enough that, you know, the distance between the surface and the center aren't really that significant. But technically, we're still talking about center to center. F is the force, or at least it's the magnitude of the force, measured in newtons. What do we mean by the magnitude? Yeah, it's the absolute value. Force is a vector. There is a direction associated with it. It's either attractive or repulsive, left or right. But we're saying that this equation isn't going to get that direction for us. Just like last year with centripetal force, if you remember that. When we solved for centripetal force in physics 20, we only got the magnitude of it. We knew that it pointed toward the center of the circle, but the equation didn't tell me that. I just had to know that. This is the same. Okay, the equation, there is a direction with the force, but the equation doesn't tell me what it is. That's okay. We know what it is, right? If it's two positives, then it's going to be an attractive force. If it's positive and negative, it's going to be two positives, it's going to be repulsive. If it's positive and negative, it's going to be attractive. We can figure out the direction of the force without an equation. And finally, K. This is the real new one here. K is a constant called Coulomb's constant. And the value of Coulomb's constant is 8.99 times 10 to the 9 Newton times meter squared over Coulomb squared. That's on your data sheet, so don't worry about memorizing that. This equation should look a lot like Newton's law of universal gravitation that we saw in physics 20. Similarities certainly in the structure of the equation. KQ1, Q2 over R squared versus GM1, M2 over R squared. They're both what we call inverse square relationships because the force is inversely related to the square of the distance, inverse square. But you can see clear differences as well, right? The direction of the force is different. The magnitude of the force is different. Do you remember from yesterday which one's a bigger force? Which one's the bigger force, electricity or gravity? Electricity. Yeah, electricity is the bigger force. Just got a little summary here of the comparison of these two forces. The relationship we just said, it's an inverse square relationship in both cases. Okay? F is equal to something times something times something over R squared. The basic structure of those two equations is the same. The magnitude of the forces. Well, gravity is a smaller force. Gravity is the smallest of all of the fundamental forces. Coulomb's law is a much bigger force than gravity is. But if you think you might forget that or get them mixed up, just look at the constants. That's a reminder for you, right? The constant for gravity is 10 to the minus 11. The constant for electricity is 10 to the positive 9. So by looking at the constants on your data sheet, that's a reminder that electricity is a stronger force. Bigger constant, bigger force. And what about the direction? Well, electricity can be attractive or repulsive. Gravity can only be attractive. The reason that gravity can only be attractive is because there's only one type of mass, positive mass. Whereas with electricity, there's two types of charge, positive and negative, which leaves open that possibility of both attraction and repulsion. Let's take a look at example number 1. Metal sphere with a positive charge of 5.5 and a mass of 2.5 is separated from an identical metal sphere, so same mass, but this one has a negative charge of 2.0 times negative 10 negative 7 by a distance of 5 centimeters. What's the electric force on the positive and the negative, and what's the acceleration of the positive charge? Picking up the red pen here, what do I want to circle? What do I want to draw attention to in this question? What is it? Absolutely, centimeters. We know we're going to have to convert that to meters. First time we're really doing calculations in Physics 30, in this unit of Physics 30. It's been a little while since we've had to do that, right? Since we did the momentum stuff. Don't forget, okay, centimeters, never use that. Meters, okay? Anything else? Anything else? Zach, you looked like you were about to raise your hand there. No? Do you see what else I might want to circle there? Identical, sure, could be identical. That's not so much what I want to draw attention to, though. Somebody said it. Yeah, in fact, we got a positive and negative charge, opposite charges. Right away, when I see positive and negative, we know that that's a force of attraction. We don't need an equation to tell me these two attract, right? We just need, well, on the first day of this unit, one of those laws of electricity that said opposite charges attract. We want to find the force on the positive, the force on the negative. We know those are going to be equal and opposite, right? If the force on the positive is 10 to the right, the force on the negative will be 10 to the left. So we only really need to find one force. And we also want to find the acceleration of one of them. So let's write down some givens here. We're going to say Q1 is 5.50 times 10 to the minus 7. And Q2 is negative 2.00 times 10 to the minus 7. Although we could very easily reverse those because it doesn't matter which one's Q1 and which one's Q2. The mass of object 1 and the mass of object 2, because they're the same, is 2.5 times 10 to the negative 3 kilograms. The distance that separates them is 0.050 meters. It's 5 divided by 100. We want to find the force. So let's do that now. KQ1, Q2 over R squared. 8.99 times 10 to the 9 times 5.5 times 10 to the negative 7 times 2.0 times 10 to the negative 7. Notice that I've dropped the sign of the charge in that equation. It's a negative charge, but I didn't put that in there. Whenever you put a negative into an equation, I want it to mean direction. This doesn't mean direction, right? That negative is a type of charge. Any equation that you use with charge, drop the sign of the charge. The sign of it's important to know that they attract, but that's all it's important for. Never include the sign. You'll see as we move forward with Coulomb's law, not so much today, but in the coming days, the confusion that that can lead to when I put in the negative. So just to avoid confusion, it's going to pop up, just drop the negative. R is 0.050, and we square that. We solve for the force here, and we end up getting 3.9556 times 10 to the minus 1 newtons, which we're going to round to how many digits? This is 3, this is 3, this is 3, this one is, I don't care. Why don't I care? Because I didn't use it. Final answer should be 3 digits, right? So we're going to say 1, 2, 3, and then let's look at the 4th digit. Okay, if we're trying to solve the 3 digits, look at the 4th digit, and look at that 4th digit, determine whether it's a 5 or above. If it's 5 or above, we round up. So it becomes 3.96 times 10 to the minus 1 newtons. 3.96 times 10 to the minus 1 newtons. Now, I want to find the acceleration. How am I going to do that? Some of you may have noticed already, this morning I added to our always wall. You want to find acceleration in physics 30? Get the force. The force needs to be with you. Once the force is with you, well, listen, once the force is with you, pretty much anything is easy, right? But particularly finding the acceleration. Once the force is with you, you can find the acceleration by saying A is equal to F over m. So our force, our unrounded force is 3.9556 times 10 to the minus 1 newtons divided by the mass, which is 2.5 times 10 to the minus 3. Now we're going to round this to 2 digits because we've got a mass in 2 digits there. I get 1.6 times 10 to the 2 meters per second squared. So my force is 3.96 times 10 to the minus 1. I should have wrote that it's attractive on both of them. And the acceleration is 1.6 times 10 to the 2 meters per second squared. Whenever you're asked to find acceleration in physics 30, get the force. The force needs to be with you. Whether it's an electric force or a gravity force or whatever force, you want to find acceleration, get the force, and then divide it by the mass, and then you're going to get acceleration. All right, we have about 10 minutes left, which puts you about 10 minutes ahead of the other class, which means you guys have about 10 minutes to work on some questions, 10 minutes that they didn't have. So I'm going to ask you to work on right now for the next 10 minutes worksheet number 6. There are 8 questions on that page, but I would like you to only work on questions 1 to 6 right now.